For millennia, humanity has gazed upwards. We have looked to the stars. Among those celestial wanderers, one has always held a special fascination. This is Mars, the red planet. It calls to us from across the cosmic ocean. We see it and we wonder, what secrets does it hold? The quest to understand Mars drives our relentless exploration. It is a human endeavor. Mars is a challenge, a promise, and a vital step in humanity's journey into the great unknown. From our vantage point on Earth, Mars appears as a bright, star-like object. Its intensity and color vary depending on its position relative to Earth and the Sun. Sometimes it is a brilliant jewel outshining many stars. At other times it is a more modest point of light, and ancient astronomers meticulously charted its path. They noticed its retrograde motion, a peculiar looping behavior that puzzled them for centuries. This celestial dance was a key piece of the puzzle that eventually led us to understand the true architecture of our solar system, with the Sun at its center, not the Earth. When Galileo Galilei first turned his rudimentary telescope towards Mars in the early 17th century, he saw not just a point of light, but a tiny disk. This was a revelation. It transformed Mars from a mere wanderer into a world, a place. As telescopes improved over the centuries, astronomers began to discern faint markings on its surface. They saw lighter and darker regions, and the brilliant white polar caps. These observations fueled speculation about what Mars might truly be like. Could those dark areas be vegetation? Could the polar caps be made of water ice, like Earth's? The questions mounted with each new observation. The distance between Earth and Mars is not constant. Both planets orbit the Sun, but at different speeds and distances. Earth completes its orbit in about 365 days, our year. Mars, being farther out, takes about 687 Earth days to make one trip around the Sun. This means that the distance between us can vary dramatically. It can be as little as about 55 million kilometers, or as vast as over 400 million kilometers. These orbital mechanics are crucial for planning missions to Mars. We must launch our spacecraft during specific windows when the planets are favorably aligned for the shortest, most fuel-efficient journey. One such favorable alignment is called opposition. This occurs when Mars is on the opposite side of Earth from the Sun. During opposition, Mars is relatively close to Earth, appears brighter in our sky, and is visible for most of the night. These events happen roughly every 26 months. It is around these times that most Mars missions are launched, taking advantage of the shorter travel time. Understanding these cosmic rhythms is fundamental to our exploration. It is the celestial clockwork that dictates when we can reach out and touch our rusty neighbor, sending our robotic envoys on their long voyages. Mars is undeniably red thanks to iron oxide, or rust. This fine, talcum-like dust covers everything. Mars also boasts colossal geology. Olympus Mons, the largest volcano in the solar system, stands 22 kilometers high. Valles Marineris, a canyon system, dwarfs Earth's Grand Canyon. Evidence of ancient water is clear, with dried riverbeds and lake beds. Mars' polar caps are made of water ice and dry ice, changing with the seasons. Imagine standing on Mars. The sky above would not be the rich blue we are accustomed to on Earth. Instead, it would often appear a pale pink or butterscotch color. This is due to the fine reddish dust particles suspended in its atmosphere. And that atmosphere itself is vastly different from our own. It is incredibly thin. The atmospheric pressure at the Martian surface is only about 0.6% of Earth's sea level pressure. This is equivalent to the pressure found at an altitude of about 35 kilometers above Earth's surface, far higher than airplanes fly. Such low pressure has profound implications for the planet. The Martian atmosphere is composed primarily of carbon dioxide, about 95.3%. Nitrogen makes up about 2.6%, and argon about 1.9%. There are also trace amounts of other gases, including oxygen and water vapor. But that precious oxygen we breathe, it is virtually absent on Mars in any significant quantity. The thinness and composition mean that the atmosphere offers little protection from solar and cosmic radiation. It also means that liquid water cannot persist for long on the surface today. The low pressure would cause it to quickly boil away, even at cold temperatures. Despite its thinness, the Martian atmosphere is a dynamic system. It supports weather including winds and clouds, and most dramatically, it can produce colossal dust storms. These are not your average terrestrial dust devils. Martian dust storms can begin in a localized area and then grow to encompass the entire planet. These global dust storms can last for weeks, blocking out most of the sunlight from reaching the surface. They pose a significant challenge for solar-powered rovers and for any future human explorers. Understanding how these storms form and evolve is a key area of Martian meteorology. The loss of Mars's once thicker atmosphere is a major puzzle in planetary science. Evidence suggests Mars had a more substantial atmosphere early in its history, one that could have supported liquid water on its surface and a warmer climate. Scientists believe that Mars lost its global magnetic field billions of years ago. Without this protective magnetic shield, the solar wind, a constant stream of charged particles from the Sun, gradually stripped away much of the atmosphere over eons. This atmospheric loss transformed Mars from a potentially habitable world into the cold, dry desert planet we see today, a stark reminder of planetary evolution. Section 5. The rhythms of another world, climate and seasons on Mars. Just like Earth, Mars experiences seasons due to its axial tilt of about 25.2 degrees. As Mars orbits the Sun, different parts receive varying sunlight, driving its seasons. A Martian year lasts about 687 Earth days, making its seasons twice as long. Mars is very cold, with an average temperature of -63 degrees Celsius. Equatorial summer days can reach 20 degrees Celsius, but nights drop to -73 degrees. At the poles, winter temperatures can plummet to -125 degrees Celsius. Seasonal changes affect the polar ice caps, which expand and shrink with carbon dioxide freezing and sublimation. Evidence suggests Mars was once warmer and wetter with a thicker atmosphere. Ancient riverbeds and lake beds hint at this past climate. Section 6. Mechanical Trailblazers, our robotic emissaries to Mars. Our journey to understand Mars began with telescopes, but to truly explore it, we needed to go there, not with humans initially, but with robotic emissaries. These machines are our eyes, our ears, and our hands on that distant, rusty world. The first attempts to reach Mars were made in the 1960s by the Soviet Union and the United States during the height of the space race. Many of these early missions failed, succumbing to launch failures or communication losses. Reaching Mars is hard. The journey is long and the environment is unforgiving. The first successful Mars flyby was NASA's Mariner 4 in 1965. It sent back the first close-up images of another planet, revealing a cratered, moon-like surface, which was somewhat disappointing to those hoping for a more Earth-like world. Later, Mariner missions, like Mariner 9 in 1971, became the first spacecraft to orbit another planet. Mariner 9 arrived during a global dust storm, but once the dust settled, it mapped about 85% of the Martian surface, revealing giant volcanoes and vast canyons for the first time, fundamentally changing our view of Mars. Then came the Viking program in the mid-1970s. NASA's Viking 1 and Viking 2 missions each consisted of an orbiter and a lander. In 1976, Viking 1 became the first US spacecraft to successfully land on Mars and perform its mission. The Viking landers provided stunning panoramic images of the Martian surface, analyzed soil samples, and monitored the weather. They also carried experiments designed to look for signs of life. While those experiments produced intriguing, ambiguous results, they ultimately did not provide definitive evidence of Martian life. However, the data they collected formed the foundation of our Martian knowledge for decades. The era of rovers began with NASA's Mars Pathfinder mission and its small Sojourner rover in 1997. Sojourner, about the size of a microwave oven, demonstrated the feasibility of wheeled exploration on Mars. It was followed by the much larger and more capable twin rovers, Spirit and Opportunity, which landed in 2004. Designed for 90-day missions, Spirit operated for over 6 years and Opportunity an astonishing nearly 15 years. These tenacious robots traversed miles of Martian terrain, analyzed rocks and soils, and found compelling evidence that liquid water was once present on Mars. They were true geological pioneers on another planet. Section 7, The Current Watch, Ongoing Missions and Discoveries. Today in 2025, Mars is a bustling hub of robotic activity. A fleet of sophisticated orbiters from multiple nations circles the planet. NASA's Mars Reconnaissance Orbiter, or MRO, has been a workhorse since 2006. MRO has mapped vast swathes of Mars in incredible detail. On the surface, NASA's Curiosity rover continues its meticulous investigation. Curiosity is a mobile science laboratory about the size of a small SUV. It has been slowly climbing Mount Sharp, analyzing rock and soil samples. Curiosity has found evidence of ancient lakes and organic molecules. Joining Curiosity is NASA's Perseverance rover, which landed in Jezero Crater in February 2021. Jezero Crater is believed to have once held a lake and a river delta. Perseverance is collecting rock and soil samples for a future Mars sample return mission. This joint NASA-ESA endeavor aims to bring these samples back to Earth. Perseverance also carried the Ingenuity helicopter, the first aircraft to achieve powered, controlled flight on another planet. Ingenuity has far exceeded its original mission, performing dozens of flights. Ingenuity acts as an aerial scout for Perseverance. Beyond NASA, other nations are also active. The UAE's Hope Orbiter and China's Tianwen-1 mission are also contributing valuable data. These missions are constantly rewriting our understanding of the Red Planet. Section 8. Stepping Stones to the Stars. The Vision of Martian Colonies. The robotic exploration of Mars has been incredibly successful, revealing a world of complex geology and a history that hints at past habitability. But for many, these robots are just the precursors. The ultimate goal, the grand vision, is to send humans to Mars, not just for a fleeting visit like the Apollo missions to the Moon, but to establish a permanent human presence, a self-sustaining colony. This is a monumental undertaking, fraught with immense challenges, but it captures the imagination like few other endeavors. Why would we even attempt such a feat? NASA has long-term plans for human missions to Mars, often viewed as the horizon goal following a return to the Moon with the Artemis program. The Artemis missions aim to establish a sustainable lunar presence, which will serve as a proving ground for technologies and operational procedures needed for the much longer and more complex journey to Mars. These include advanced life support systems, radiation shielding, in-situ resource utilization, living off the land, and strategies for dealing with the psychological effects of long-duration spaceflight far from Earth. Mars is a formidable destination, typically a 6 to 9 month journey one way. Private companies are also playing a significant role in accelerating the timeline for Martian colonization. SpaceX, led by Elon Musk, has the explicit goal of making humanity a multiplanetary species, with Mars as the primary target. Their Starship vehicle is being developed as a fully reusable transportation system designed to carry large numbers of people and significant cargo to Mars. The vision is ambitious, to build a city on Mars within the coming decades. Such private initiatives are injecting new energy and a sense of urgency into the dream of Martian settlement, pushing the boundaries of what seems possible. The challenges are immense. Astronauts would face prolonged exposure to cosmic radiation, the physiological effects of microgravity during transit and reduced gravity on Mars, about 38% of Earth, the threat of Martian dust, and the need to produce their own food, water, and breathable air. The concept of terraforming Mars, transforming its climate and atmosphere to be more Earth-like, is a fascinating but incredibly long-term and perhaps even ethically debatable prospect. Yet despite these hurdles, the drive to establish a human foothold on another world is powerful, driven by a desire for exploration, scientific discovery, and perhaps the long-term survival of our species. Section 9, Our Cosmic Destiny. Why Mars beckons humanity. Why Mars? Why expend vast resources and undertake enormous risks to reach this distant world? Mars is a scientific treasure trove, holding clues to planetary evolution and climate systems. It may even answer the ultimate question, are we alone? Mars offers a reachable target for astrobiological quests and survival imperatives. Establishing a self-sufficient outpost on Mars is a backup plan for humanity. It fuels innovation and inspires future generations. Mars beckons, and it seems to be in our very nature to answer that call.